Hey everyone, welcome back. In this lesson, we're going to be talking about the hydrologic cycle. That's basically fancy words for the water cycle. So we're going to be studying the water cycle in this video. We'll look at the rock cycle in the next video, and I believe after that, maybe not the video right after that, but coming up shortly after that would be the tectonic cycle. So in this unit, we're just going to be looking at a few different cycles, and we'll throw some other stuff in there depending on how much time we have. Now, it is important to note before we really start with this lesson that I might switch between the name hydrologic cycle and the name water cycle. I'm talking about the same thing. This cycle describes how water moves across our planet. That means on the surface, beneath the surface, and above the surface in the atmosphere. So let's take a look at how the water on our planet moves. Let's get started. So water on Earth. Water is a very, very essential part of what Earth has to offer because it's essential for all life on the planet. And so what that means is that no matter whether you're an organism that needs a lot of water or just a little bit of water, water is necessary. So for some organisms, for example, fish, things that live in the ocean, aquatic organisms, they kind of depend on water because that's where they live. They live in the water. I mean, you kind of need water if you're going to live in the water, right? You need water to be present. And for some organisms, whether that's fresh water or salt water makes a difference. Depends on this, like it decides where they can live. Some organisms that can only live in fresh water won't do so well in the saltwater oceans, things like that. But the point is, organisms all need at least some quantity of water on the planet. So I guess it's good news then that if you look at this right here, the world's oceans, let's do this in blue. We're talking about water, so let's get rid of that. So the world's oceans, there's my pen. The world's oceans cover over 70% of the planet's surface. So that means if you look at a globe of the Earth, and then you got your continents on there. Let's draw in some land. We've got like Alaska right here, and then North America, there's Mexico. Going down, South America will be somewhere over there. Come back up the other side. Something like this, something like that, something like that. Let's say that there's the Americas, and then over here will be Russia, and then leading down towards China and Korea and Japan and stuff and so on. So you'll have, if you look at a globe, you'll see that there are obviously plenty of areas of the world that are covered by land, and that's the familiar continents. But there's a lot of the planet that's covered by water, and we don't talk about it as much because, you know, if you're in a class where you're studying geography in terms of countries, then the water isn't really an important part. You'll end up jumping from continent to continent without looking at the water that sits in between them, right? If you're studying the countries and you start off with the Americas and then you jump over to Europe, you ignore everything that happens in between, which is the Atlantic Ocean, right? So we kind of forget about just how much of the planet's surface is covered in water. In fact, the Pacific Ocean, so this ocean right here that's in between the Americas and Eastern Asia, it's so big that if you started off in the Pacific Ocean somewhere up here, around where that red dot is, somewhere way up there in the Pacific Ocean, and then you drilled your way through the entire Earth and popped out on the other side, you'd still be in the Pacific Ocean. It's that big that you can go straight through the planet and come out the other side and still be in the Pacific. Now, this drawing is quite a poor one. I don't mean that you just dig a little bit under the surface and pop out the other side. I mean you go from this end of the planet to this end of the planet, and I haven't drawn it well with my placement of the continents and stuff, but the Pacific Ocean is that big that you can drill from here through the center of the Earth to here and still be in the Pacific Ocean. It's an absolutely enormous body of water. And so we kind of tend to forget sometimes just how much of the planet's surface is covered in water, and given how difficult it is to study things at the bottom of the ocean, we sometimes forget how deep it is. Now, it shouldn't be a surprise that the oceans cover up a lot of the planet's surface, or that they're pretty deep, but it's also important to remember that on the scale of the entire Earth, the oceans aren't really that deep. And I'll give you some numbers, and then we can sort of think about it a little differently. To go from the center of the Earth to the surface, that distance, that radius of the planet, is about 6,371 kilometers. The oceans go down about 11 kilometers-ish. At their deepest point, it's around 11 kilometers, which is really kind of nothing compared to the size of the planet. But at the same time, Mount Everest is 8,848-ish meters tall, so about 8.8, almost 9 kilometers tall. So the deepest parts of the ocean are farther away from the surface than the top of Mount Everest is, sure, but on the scale of the entire planet, it's really quite a smooth ball. The difference in heights and the difference in elevation compared to the size of the planet as a whole is really, really quite small. So that's just something to keep in mind, that as much as we think, oh, most of the planet's surface is covered in water, sure, that's true, but most of the planet doesn't have any water at all. So it's important to keep that in mind, just as a sense of perspective, so that you're not surprised if you hear something later about how little water the planet has. But anyway, so an important point about the water on our planet is that even though 70% of the planet's surface is covered in water, most of that water is salt water. Only a couple of percent, only 2.5%-ish of Earth's water is fresh water, and that's what we use, that's what we humans use, and there are plenty of other organisms that depend on fresh water. Now, if that wasn't bad enough, saying that, oh, most of the planet's surface is covered in water, but most of it's not useful to us, then it gets even worse. Out of that 2.5%, most of that is inaccessible to us. It's stuff we can't really get to. It's locked up in glaciers, it's locked up in ice sheets, in places that are hard to get to, Antarctica, Greenland, places like that. And so out of this 2.5%, only 1% out of that 2.5% is water that we can use. And that's the water that the whole world is relying on. And so that's why, if you've ever seen in the news, especially in the last couple of years, where cities like, I want to say it was Cape Town in South Africa, was having a water crisis. And it might sound a little bit strange that, our whole planet is covered in water, yet we're having a water crisis. This is why. Most of that water is not the water that we use, and of the water that we can use, we can't get to most of it. So we're really working with a fraction of what it looks like when you look at a globe like this. We're not really using all of that water that we see. But yeah, now let's talk about, so here we've talked about the importance of water and kind of how much there is, how easy it is to get to. But now let's talk about how it moves in and around the planet. That's the subject of this lesson. So here's a diagram of the water cycle. It's not the most complicated diagram that you'll see. Actually, I think I have a more complicated one, just a slide or two after this, for us to take a look at. But basically, this is a simple diagram of the water cycle. It covers some of the main sort of features. So if you start with a body of water, let me do this in something like red, just so that it stands out against the blue. So we've got this body of water here. It could be a lake, could be a sea, could be an ocean, etc. This body of water, the water is heated by the sun, and it evaporates. So it travels up into the atmosphere. It goes from a liquid to a gas and travels upward into the atmosphere. And then up in the upper atmosphere, it cools down and condenses. And this is what leads to the formation of clouds. Now, another contributor to the formation of clouds is transpiration, which is the mechanism by which plants expel the water that they're not using anymore. And if you've got any plants just kind of sitting around in your house, what you might be able to notice from time to time is little drops of water forming on the edges of the leaves. I actually have a picture that I didn't think to include in this lesson, but when we have our next live session on Zoom, I will show you guys there a picture of this sort of transpiration as it happens. But anyway, so the water gets from one way or another, either from plants or just from normal evaporation from bodies of water, gets up into the upper atmosphere, and then that's where it forms clouds, and then those clouds eventually precipitate that water back down to the surface through rain or snow. So that's this precipitation right here. And then we've got these two things right here. We've got groundwater and we've got surface runoff. So basically, after precipitation, you've got a bunch of water on the surface. You've got this water here, you've got this water flowing down the sides of the mountain there. And basically, surface runoff is water that travels along the surface of Earth to get back to a bigger body of water. So let's say it rains down on this mountain, and then now we'll do this in dark blue and you can just follow the line. And then it's flowing down the surface of the mountain, and then it reaches this little stream right here. It goes into this body of water, and then maybe it continues out and reaches a body of water like that, and then travels all the way back to the ocean. So you might be able to see the water follow a path that it's rained down, starts here, and then it travels along the surface all the way back to the ocean. That's a possible route. It's not always going to be back to the ocean. If the water, for instance, if it freezes, if it snows down, it might just sit on this mountaintop for a really, really long time. But another option is that it doesn't continually flow along the surface. Some of it will seep underground. It'll seep into the soil below, and we'll talk about this in a few minutes. And that's where it ends up being stored as groundwater. And the reason I say stored is that, oh, you can't see that line at all. Groundwater, there we go. And the reason I say stored is that water moves very, very slowly when it's in the subsurface, which is where the groundwater is. Subsurface meaning below the surface of the planet. That's where the groundwater is stored, and it moves really, really slowly through there. So that's why I'm saying stored. So here's another diagram of the water cycle. This has a lot more kind of itty-bitty details that we can look at. I'm not going to highlight all of them. This is more for you guys. You can pause the video here. You can take a look at them. You can see, oh, you know, I've heard of this thing before, or oh, I've seen this happen before, or oh, I remember this from somebody else's geography class. So there are some of the same kind of ideas as what we just talked about. We've got evaporation here, we've got evapotranspiration here, we've got condensation, we've got precipitation, we've got runoff, right? This doesn't say surface runoff, it has snowmelt runoff, but same idea. Here we've got surface runoff, we've got more evaporation, we've got more precipitation, etc. Right? We've got things, oh, down here we've got groundwater, right here, down here, and down here. And of course we've got the oceans, the large reservoirs of water, the oceans and the lakes that are storing all of this water. But so you can see here that there are a lot of the same ideas as on the previous slide. We've just got some extra things. So instead of a simple, oh yeah, the water just goes back to a lake or an ocean, it's differentiating between things like rivers and wetlands and different types of lakes, right? We've got saltwater lakes, we've got freshwater lakes, things like that. Oceans, we've got vents at the bottom of the ocean that spew out all kinds of material, and surely water is in that as well. We've got steam from volcanoes. So there are lots and lots of different places that water might find its way during its, journey through the atmosphere and back down to the earth. But basically it's all the same ideas. The arrows are telling you the direction in which the water is moving. So for example, a downwards arrow means it's going from the atmosphere towards the surface. So precipitation there, or dew down here, or fog drip, or deposition. These kinds of things here are showing where it's going from the atmosphere to the surface, or perhaps from the surface to the subsurface, like this infiltration right here. And then we've got the same thing the other way around, right? We've got evaporation and evapotranspiration have straight upward lines like this. We've got sublimation, straight upward line there. We've got plant uptake. This one looks more like it's going from the subsurface to the surface, and then that water will end up being transpired, right, from transpiration right there. That water will end up being transpired and sent back upwards to the atmosphere once again. So these arrows are trying to direct you to where the water is found and where it goes from where it is, right? You've got some of our surface runoff, we've got some of our groundwater, we've got all different kinds of things that you can basically go back to the point where I hadn't drawn all over this picture, and you can pause it there and you can just take a look at this. You'll see all the different things that are part of the water cycle. This is just a more complicated version of what we saw on the last slide. So for the rest of this lesson, we're not going to go into a ton of detail on any of them, but I just want to talk a little bit about each of these different points. We're not going to go into a ton of detail because I feel like a lot of this is stuff that you already know. But just for the completeness of our unit, I want to make sure that we cover the water cycle at some point. And maybe there's something that you don't know that we cover in here. But we're going to talk a little bit about each of these different components. And if I'm not mistaken, we're going to go in this exact order. So we'll start with evapotranspiration, then we'll look at condensation, precipitation, infiltration, and runoff. Some of it might be a little bit new. I remember when I was in school, we definitely didn't talk about stuff like infiltration that much. And runoff, I think we talked about it, but not nearly as much as we talked about things like precipitation, condensation, and evapotranspiration, or really just the evaporation part of it was sort of our main focus. But we're going to talk about all these things. So, as we've mentioned already, evapotranspiration is a combination of evaporation and transpiration. Now, evaporation is just the process of water going from being a liquid to being a gas, right? So steam is basically the product that you get out of this. So if you have boiling water in a pot and you heat it up, you'll end up with steam that then rises as a gas, right? It turns into water vapor and it rises. And so that is the process of evaporation. Now, in oceans and lakes and things like that, you'll have the sunlight beaming down all day if it's a sunny day, and even if it's not a sunny day, it might be quite warm in some places. But if we think about it as sunny days, hot days, the water can get quite warm, and because the water is transparent, so you'll have your body of water like this, and it goes down a long way, and then we've got our sun up here. Right, there's the sun, something like that. Bam, there's our sun. Then of course the sun is beaming down its rays onto the surface, and it's hitting a whole bunch of this water on the surface, right? 70% of the planet's surface is water, so most of that sunlight is just going to be hitting the oceans. But the oceans aren't quite the same as land. As you might have noticed, when it's a really hot day and the sun is beaming down on the roads, they get really warm. The roads get warm, the ground gets warm, just in general. When it's hot, it's hot to be on the ground. Um, and you'll notice that if you're, if you're on the street without shoes on, you'll notice that difference in the temperature. But in water, it's not exactly the same thing, and the reason for that is that water is transparent. So the light and the heat comes down and hits the surface of the ocean, but a lot of that energy continues to travel into deeper layers of the ocean. So instead of that amount of sunlight, so on land, if that amount of sunlight hits land right here, right, and we've got rays from the sun that come in and hit the land. Oh, I drew that wrong. Hang on, let's redraw. Let's fix that. So we've got our rays from the sun, and they come here, and they hit the land right here. That's only really warming the surface, and it's heating up this same tiny part of the surface over and over again. And that's, of course, that's happening all the way across the surface, but it's not really going any deeper. The soil and stuff that's down here isn't getting any of that sunlight, so it stays relatively cool. The surface, on the other hand, is collecting all of that energy and gets really, really hot. In the water, that doesn't happen so much. Because the water is transparent, a lot of that energy dissipates and goes deeper into the ocean, and it's not going to be as strong the deeper it goes, right? The more water it has to travel through, the less it'll heat it up. But that energy does go a much, much deeper way into the ocean, so we don't see as much evaporation as we would as if it was just the surface that's being heated, and that's because it goes a long way through. But still, it is that energy from the sun that's responsible for this heating of the surface, and then that water evaporates. Transpiration is basically a special form of evaporation, and basically, to draw what I was talking about a couple minutes ago, if you've got a plant leaf, like so let's draw a leaf, something like this, and same thing on the other side, something like that, then what you might see, if you look at the right time, is you might see a little water droplet like this, just sort of hanging off the edge of the leaf. And that's this water that collects basically in like drop by drop and then evaporates away from the plant. And so this is a very plant-specific version of regular evaporation. And so if we take regular evaporation from the oceans and lakes and seas and all of that, and we combine it with all of the water that's contributed by plants, it's not necessarily a lot. It's like, what, one drop at a time? That's nothing. Sure, but if you've got all the plants doing that all the time, or a lot of the time, that's gonna amount to a significant amount of water, right? If you say one drop of water is basically nothing, sure, but if you have a billion plants that are all, contributing one drop's worth, even if it was one drop per day for a billion different plant organisms, a billion drops isn't nothing, and it's something that needs to be taken into account. If it's more than a drop a day, if it's more than a billion plants, then that number gets even bigger, right? So that's why we have to sort of add it into this discussion. And so when we merge the two, evaporation and transpiration, we get evapotranspiration. So now let's talk about condensation. So condensation happens when the evaporated water, so it's in a gas phase right now, turns back into a liquid. And this happens when the surrounding environment is really cold. So basically what happens here, so I've got this picture of a can of Pepsi or something. If it's not Pepsi, I don't know what it is. But you can see these droplets on you can see these droplets forming on the outside of the can. So if you ever had a cold drink in a bottle or a can on a hot day, you'll notice that the outside of the bottle or can or whatever, the outside of the container gets wet. And that's because of this condensation. Water vapor from the atmosphere that's really, really close to the edge of that bottle or can senses that it's become a lot colder, and then it condenses and attaches itself to the edge of the can. That's a really simplified and not entirely accurate description, but it's just to give you an idea of what this condensation process is. And basically that's what happens in the upper layers of the atmosphere, because it starts to get colder as you go upwards in the atmosphere, and so then these water droplets are suddenly in a cold environment, so they condense and they form clouds. And so it's actually really interesting. If you Google pictures of condensation, I picked this one in particular so that you can see the droplets really clearly. But if you look up pictures of condensation, you'll see something like somebody's got a can of Coke or something, and the droplets are incredibly tiny, incredibly uniform little circles that cover the entire thing, almost so small and perfect that you don't even realize that there are droplets on the surface of the can. And it just covers the entire thing in these very, very small, very regular patterns. And that's something you can look up on your own time. Some of them definitely don't look like they're real, but I've seen myself, if you leave something out like that, on a hot day, if you leave a can of something out on a hot day, then yeah, it can begin to form these really, really small droplets. But yeah, anyway, so this process of condensation is what leads to the formation of clouds, and it's what turns the water from being completely just this water vapor gas back into droplets. Now, the next thing that happens is that those droplets coalesce, they combine, they combine to form larger and larger droplets. And so when those droplets combine to form larger drops, they basically get heavy enough that they can't be suspended in the air anymore, right? Tiny amounts of water in the form of water vapor and steam and stuff, you can see that it's light enough that it can just float up into the atmosphere and just dissipate there. But if I had an actual large drop of water on my finger and I tap my finger, it's going to fall to the ground. It's not going to suspend itself in the air and just kind of hang around there. Once they get heavy enough, they can't stay suspended in the atmosphere and they come back down to the ground. And so basically clouds grow due to that condensation process, and then the water droplets in there grow to form these drops, which then rain back down to Earth. And of course, if it's colder, then they'll come back down to the ground as snow. And so precipitation is the mechanism that lets the water come back down to the surface after being super high up in the atmosphere. And there's a fun fact. I think if you do the math, there's some debate on whether or not it would be deadly. But several years ago, I did hear for the first time that if you didn't have air resistance to stop the raindrops from accelerating as they travel downwards from the clouds, they would be able to kill you on impact just because of the speed that they hit you at. So the fact that we have an atmosphere to slow down the raindrops is what makes rain not hurt a lot when the droplets hit you. So that's just a fun fact. You don't really have to do any of the math. That's more of a physics calculation, but being a student of physics, I had to mention it. So the next part is infiltration and runoff, and this is basically, these are the two things that tend to happen once the water has reached the surface. So let's say you've got like a hill, and then it goes down here, and let's say you've got a body of water like the ocean that starts over there, and we've got a cloud, which I can draw in white as if it's in that green section there. So we've got our cloud, and let's say our cloud rains down some water onto this hill. Now the water has two paths. It can either travel along the surface as runoff, or I'll do this in a different color, I'll do it in purple, or it can seep into the subsurface. It can travel below ground, and so this seeping into the subsurface part is called infiltration, and then it is stored in the ground as groundwater, and then that groundwater can either come back up to the surface at some point or come back out when it reaches a body of water like that in the ocean. And so so the water, a lot of times the water can enter the subsurface, but if it's already been raining a lot, then basically all the soil is saturated. And what that means is basically if you've got if you zoom in a lot and you look at the tiny, tiny grains of dirt and stuff in the soil, the dirt grains have little gaps in between them. They're not like little cubes stacked on top of one another with no spaces. They have these gaps in between them. And basically what happens is when it rains a lot, these gaps, instead of being filled with air, fill up with water. So you'll end up with water in all these gaps here. And so if that happens, then if any more water were to seep into the subsurface, there'd be no place for it to really go. So oftentimes after it rains a lot, you'll end up with more water just flowing on the surface, and this can be what leads to intense flooding after really, really heavy rain, is that the water stops distributing itself between the surface and the subsurface, and it starts to all just flow along the surface. And then eventually, either by traveling through the ground or along the surface, it eventually collects. All the water collects in streams, lakes, rivers, and oceans. That line for rivers went right through the word rivers, so let's try that again. Right there, rivers. Like so. Something like that. And yeah, groundwater also moves, but it's a much slower process than the water at the surface, and it actually moves in some interesting ways. I took a course on groundwater last summer. It was really interesting because we tend to think, and what we see on the surface is that water will flow, if you have a hill, the water will flow from a higher point on the slope to a lower point on the slope, and it's basically being pulled along by gravity. In the subsurface, it's all about the different pressures. If you've got low pressure in the groundwater here, if you've got a low pressure here, and you've got a higher pressure in the groundwater here, the water would actually flow that way, because it wants to flow from high pressure to low pressure, high concentration to low concentration type stuff. And so it's interesting that groundwater doesn't really follow all the same rules, because it's subject to different kind of influences from the environment, like this stuff with being saturated. We don't really see that on the surface. It just flows along the surface. There's no big deal. In the groundwater, in the subsurface, it's a different story. And that's something that, if you guys are interested in, we can talk about a substantial amount more. Like I said, I took a course on this last summer. I'm by no means an expert in groundwater, but I definitely know a lot more about it than I did before I took that course. Because before I took that course, I knew nothing. But yeah, so these are basically the two main paths that water tends to take once it's reached the surface again and is looking to get to one of those bigger bodies of water. Now, of course, sometimes the water will get trapped in the form of snow, and then it doesn't do any of this. It doesn't move anywhere. It just sits there as part of a mountain snow cap, or gets stuck in a glacier, and it doesn't move for thousands of years sometimes. So this, like I said, it's not been an all-encompassing discussion of what happens to water on the planet, but it should give you a good idea of how water moves around our planet's surface and subsurface. So once again, I'm just putting the slide back here, not really with anything to add, but just so that you can pause and contemplate. You can look at the different arrows on this diagram and think about, well, okay, what did I know before I watched this lesson, and what have I learned now? Do I know anything more about transpiration? Do I know anything more about runoff? Do I have a better idea of what groundwater is? Things like that. So this slide is just here for you to, if you want to pause the video, think about it, and that's about it. Same deal here. Just a copy paste of the slide from earlier. Same picture, nothing new here, but now once again you can hopefully appreciate this diagram a little bit more. Things like the infiltration and groundwater processes, hopefully you understand a little bit better. And of course we didn't talk about everything here. I haven't talked about wetlands, I haven't talked about sublimation and deposition, I haven't talked about the saltwater lakes, I haven't talked about permafrost all that much. I didn't talk about the thermal vents at the bottom of the ocean. So yeah, there's definitely stuff that I've left out of this discussion, but hopefully from this picture and from the rest of this lesson, you have a pretty good understanding of the water cycle, and hopefully you learn something new about some components of the water cycle. And that's it for this lesson. Our next lesson is going to be on the rock cycle. For some of you, you remember that whenever we talked about rocks in our geology unit a couple of years ago, we always had this guy as a special guest. So he's back. And hopefully you guys will enjoy some of the amusing little things that I've put in the next lesson. So if you have any questions, of course, about the water cycle, please let me know, either in a comment or in an email or on the Google Classroom. Some of you have me on Instagram, some of you have me on Facebook, whatever. Anything that's convenient for you, send me a message, and I will be more than happy to clarify any doubts that you guys have. I think that's everything, so I will see you all in the next video. Have a good one.